Angelika Elderbrook.
I'm Jake Schwatter.
Alex Bastine.
We are from the University of Evansville, and we're here today to talk about the predictive analysis of the Association of Tennis Professionals tennis data. So just as an introduction, tennis is a sport where the players hit a ball over the net into the opponent's court, trying to win points by making it difficult for the opponent to return. Matches are played in games and sets. The winner is the first player who meets the required amount of wins for the sets, with special rules having to do with ties. So to win a tennis match, you must win at least 6 games with a 2-game difference. If both players win 6 games, that is when the set goes into a tiebreaker, and players must win 2 or 3 sets to win a match. We will be using topological data analysis to study the shape of the data and to help us interpret the noisy data.
So this is our lower star filtration graph. We get this from our G function, which we developed and we'll explain more on a later slide. And from that we get a graph. And from that graph we get certain values for our nodes that we'll use for our persistence diagram and with our, pretty much our filtering. So we'll see that each node, like 1 through 10, it has a weight associated with it. And between an edge, whichever of the edges has the highest value, of the nodes that has the highest value, that will be the edge. And in the case where a triangle is formed, we look at which of the 3 edges has the highest value, and that will be the area of the triangle. And from that we get our persistence diagram. This pretty much shows the period in which a feature exists and comes out of existence in a diagram. The Betty 0 represents our connected components, and the Betty 1 is our poles. And technically it goes on until 1, but that's just where it stops. It's not necessarily that it dies at that time. And this is the G function that we developed. We wanted a way to calculate the win rate of any player, the age of the player, and the number of matches played by a given player. So for our win rate, it's the wins of the player divided by the matches played by the player, and the number of matches is the wins of the player divided by the total matches, whether the player played or not. And we found this weight we determined by the age, which we just found out by kind of like doing some plugging and chugging pretty much. It's this equation, and then it's to the power of 18.5 minus y. And y in this case scenario is pretty much when the player was playing between 2000 and 2025. Like for example, when y is equal to 1, that means they played in 2001. And we take the maximum of the wins of that player in that year times the matches of that player in that year divided by the wins of the player times the matches of the player in total throughout their whole year. And from that we got our G function, which is our weight times the wins of the player squared divided by the matches of the player times the total matches played.
So then for that, to use it in a statistical model, we need to get a single number from this process of lower star filtration. So from the graph, we do lower star filtration, and then we get the persistence diagram that you saw earlier. And then from the persistence diagram, we take a set number of intervals that are equally spaced, and we calculate how many intervals are there on average within that interval. And we do this separately for Betty 0 and Betty 1, because that's just how it works. And then from that, we also have to take reference graphs. So the reference graphs can be pretty much anything, which we'll explain what those reference graphs are on the next slide. But you need at least 2 reference graphs, preferably more, and you calculate the persistence diagram and the vector of average Bettys, or I'm just going to call it the vector from now on. And what you do is you take your main vector and compare it to any two reference graphs and reference vectors. And you see if that main vector is within the interval created by the two reference vectors. If it is, you add 1. If not, you add 0, and then you divide by the length of the vector. Now you do this for every combination of pairs of reference graphs, and you divide it by the number of pairs to get a single number between 0 and 1 that you then can use in a model. Now for our use in our first lower self-filtration model, we had 9 reference graphs, 3 which come from the local graphs of each player, as well as 3 matches that are randomly selected and are constant and are the same for every single comparison in every single match that we use. And we also have a step of t is 0.001 for our calculation of our vector. Now we also have some other graph-based indices and numbers for our model, which are the geometric arithmetic index, the Randic index, and the number of nodes and edges. We also have the g-value difference, though that's not always the case, as we created a model that uses it as a variable and then it for direction. For direction, it's basically, we assume that the player with the higher value is going to be the better player. And as you can see here, the one that uses it as direction tends to do better with it having a higher accuracy in all 3 models that we use and tested on. With, in this case, method 2 being the best, with the model, the XGBoost model, having about a 61.3% accuracy. Now, this model has a lot of issues. We only trained it about 900 matches with about 300 used for cross-validation, while our total data has about 66,000 unique matches from 2000 to 2025. And we also, for potential improvements, want to use more data, as well as other graphical indices or centrality indices and topological measures, as well as having cleaner data, as there are some errors with the names in the database of how it's entered, which I try to fix, but it just caused a lot of other problems, and I don't understand why. Then we created a second model using other topological summaries, which these are 3 experimental summaries, HNav being based off the average velocity given through a persistent diagram, and then HWNav and OWHNPV are other things that are the other summaries that are similar, but are built off HNav to try to fix some of the errors that were found with that summary. We also added other direct topological summaries, basically the mean and standard deviation of these vectors, as well as added the difference in ATP rank as a variable, and more graph-based summaries like PageRank, and also used the entire data set for this model. Now, as you can see, it is very much better. It has about a 5 to 6% improvement rate, with the best one being Random Forest this time, with about a 66.2% accuracy rate. And it's much better and perform much better under cross-validation. But there is some problems with this model. The rank difference is about 30% or 36% of the importance in the model, and it doesn't really come from the graph-based measures and indices that we actually want to use. So that caused a lot of problems in the ease of use on the comparisons. Though the new centrality measures and the direct topological measures come about to 42% of the importance in the model. So we want to use that in a future model using the first model as a base to try to get an even higher accuracy than 66%. Also, no Betty 1 information was used in this model, which could have caused a lot of problems as well.
All right, so while we were developing the topological models, we also wanted to compare it to a purely graph theoretic model for predicting tennis matches. So this is a much simpler model and using just graph data. So here, the CATS index was introduced however long ago as an index for graph theory, and here A of K is the adjacency matrix of the graph, and beta is an exponential dampener. And essentially what this does is A of K of U V tells us how many paths there are of length K between the vertices U and V. So essentially, the bigger the CATS index, the closer together the vertices are in the graph, is how we can think of it. So then we adapted this. You can use the exact same formula for a weighted digraph, and it turns out that can be very useful in predicting tennis matches. So this is an example of the CATS similarity index. In this graph right here, right, we have one path of length 2, so 0.5 squared times 1 if our beta is equal to 0.5. 2 paths of length 3, so 0.5 to the third times 2. 1 path of length 4, 0.5 to the fourth times 1, and that gives us our CATS index. So the bigger the number, the closer together the vertices are, and the more tightly linked they are. So then we, using our directed version of the CATS index, we developed the CATS score, which is the difference between the CATS index from U to V the directed CATS index from U to V and the directed CATS index from V to U. Basically, this tells us how much better of a player U is than V. If this is positive, U is a better player than V. If it's negative, V is a better player than U. So then we use the score to create a predictive model. We weighted we put an edge from player A to player B if player A is defeated player B in a tennis set, and then we weighted each edge by this much. We did some bit of experimentation. This is the best way to weight the edges that we found. And then once we had our edge weights and we had our CAT scores, we used that to create a predictive model. And this is our model. Bit of a mess, but essentially CAT score here is the CAT score from player A to player B. And if the CAT score is 0, then the probabilities are the same. If it's greater than 0, then the probability is greater than 1/2. That player A wins. If it's less than 0, less than 1/2. And so we have this. So how about our results? When we were using cross-validation to develop this model, these were the results we had: accuracy 54%, and then standard deviation, AUC standard deviation, and so on. And then we set aside data from 2023 to 2025, I believe, to test the model on. We didn't use that for training. But when we tested the model, we tested it by year and then overall, and these are our results. These are the population sizes, and accuracy right around 62% for all of them, you can see. So pretty solid considering that it only takes into account the structure of the graph. So that's all. Oh, yeah, what was I saying? Possible improvements for the CATS index. So we very much simplified the calculations of the CATS index in a lot of different ways because it is still a heavy program. It takes a lot of time to run. So we had to simplify it to speed it up. That probably ruined the accuracy of it, lowered the accuracy of it a bit. If we had more powerful computers, we could probably make it more accurate. And if we had a larger data set, of course, we'd have more connections between players, which would give us more information. So that'd be better. And
Now, we wanted to compare these models, but when comparing them, I found a very interesting pattern between them. When testing on a tournament, we used qualification rounds and official tournament rounds. And we found that when split down the middle, when the models agree, we use that. And if they disagree, then if it's split down the middle, the earlier matches using low star filtration and the later matches using CATS index, if we follow that formula, we had an accuracy of up to even maybe higher than 90%. So we then created a model to use the remaining data from 2025 as our training data for both CATS and lower star filtration only went up to US Open, which was about in September of 2025. So we tested it on the remaining data of 2025, but the main problem is that when testing, the data set doesn't have qualification rounds, and that 50-50 split with the 0.5 doesn't work because we don't have the qualification rounds. So we started testing other separation values, which is the current round divided by total number of rounds in the tournament, which the one that we have up here is when it's less than or equal to 0.4. So when the value of current round divided by total round is 0.4, we use low star filtration, otherwise we use CATS index. We found an accuracy of about, if I can get this here, 63.5%, which is better than the lower star filtration cross-validation and the CATS post-validation with the 2023 to 2025 data, though not by much, and we hope to improve it more and testing more intervals as well, and maybe even with the new lower star filtration model that we are actively working on. Any questions?
Let's thank our speaker first.